Okay, as a mark here, if decide to use an autoencoder, the one of the advantages for this model is we don't need to do any manual annotation or label. Okay, that's the good thing about it. Always remember the input or the output should be the same as the input. That's it. Okay. And I also mentioned here, if we apply the MLP multi-layer perceptron with if the input is a vector value data, we can use it for dimension reduction, entity embedding, and missing value handling. Okay. I'm kind of too slow. Since we are here, let me just do it very quickly for you for missing value handling. Okay. Suppose we have an x1, x2, and up to xp. Okay, feature. Okay, we have a feature. Then we do a lot of MLP, multi-layer perceptron. Okay, and then after that, as I keep saying, for the autoencoder, the output should be also the same as the input, so that the output, we will expect out the output. Now for some sample, okay, if for some sample we got x1, x2, whoops, we lost x. Okay, we have the missing value here. Okay, for x3, now how to do it? First, you collect all the samples that have complete vector. Okay, when I say complete, which means what? There's no missing value. All the samples, they have the complete information for each individual feature. 比如说你第一个你训练的资料里面呢，先把那个有 missing value 的拿走，把那个有完整资料的呢拿来喂，听得懂 ？Which means we have the ground truth. This is the ground truth. Okay, we have the true value. We know something as the ground truth. And then what? Even for this case, don't use this example, okay, to train your model. But we train all the samples that have complete vectors, okay, complete vectors. Now, in case we lost most of the X3 feature, there could be edges, okay, because a lot of people might take it as a secret. I won't tell you the edges, right? Okay. So, in that case, what can you do here? We assign it to be 0. Okay, we assign 0 to X3. But however, for this sample, I have the exact value. You know the true value of X3, right? We just block. This is called mask. Okay, we just mask X3, which means we assign 0 to X3. So after you train the model, now when you have the missing value here, then you put it here. Okay? Then you can X3 as your estimated value for this feature with missing value. Everyone follow? 第一个你训练资料要把有 missing value 那个样本先拿走， 把有完整的所有的资料、所有的 feature 都有的那些样本呢，你当成输入输出。可是，在训练的时候呢，你故意要把那个有 missing value 的那个 feature 呢，把它设为零 ，equal mask。Okay? Everyone follow what I'm saying? And then we use this autoencoder model to estimate what could be the output at 3. Okay? Actually, you can call this as a mask autoencoder. This is a partial technique used in ChatGPT. ChatGPT 是这样用的，有一部分不是说全部。It says what? For example, say I am a student. Then you go for the MLP. Well, actually, for ChatGPT, it does not use MLP. Okay, I put it on neural network, and the output. Okay, then you say so when you do the training, you will mask. For example, I mask M. I put 0 here. Just say I'm a student, but I give you the output, okay? Give the ground truth output, which is I am a student. Then you will estimate what should be. When you read I, and then you will estimate what could be the probability that the next word after I should be am. As you know, you can use softmax, right, to evaluate the probability. What could be the word following I? Well, actually, it could be, say, I see, right? It may not be M, but anyway, it will give the probability. That's why when you ask ChatGPT, you even with exactly the same question, okay, the same prompt, you won't get exactly the same answer, right? Because that's something, everything is based on the probability. That's one of the techniques. I didn't say, okay, one of the techniques, it learns, okay, it learns how to respond the question, okay? Then you will generate a sequence of the sentence based on the probability or based on what it has so far, and you will look for the right sentence or the right word or the right phrases, okay, that will fill in something is missing, okay. Anyway, that's the mask. So first you can use this for entity embedding. Now let's come to the missing value. Now let's come to the entity embedding. Suppose it's one hot encoding, right? Suppose x1 is 0, x2 is 1, and all other must be 0, right? There's only one element has the value of 1. All others must have the value of 0. Okay, one hot encoding. Okay, so for this sample, it might indicate this sample belongs to class 2, for example. Now, what it learned here is this is the embed. Okay, because the expected output must be also 0, 1, and 0, and all the way to the 0. Okay, then, so the compressed output will be the hidden variable which we use it as the embedding, and the value will be a real number. This is another way to do the thing, okay, for embedding. Everyone know what I'm saying? Now, here's another way we can do the embedding. Simply just by MLP, okay? Suppose we have they are the continuous or numerical variable, okay? This is a numerical. Let me just put or real number, okay? Real number, such as the weight, the height. Now here we have, suppose we have a called C1, which is categorical variable. Okay, we have a categorical variable. And then we code it as one-hot encoding. Okay, one-hot encoding. Now, the C1, we put it as one-hot encoding, called C. Then we have a variable C. Then we put it to be C1, C2. Okay, suppose CD. D is the what? The dimension, right? The dimension. The entity embedding dimension we want to reduce, okay? And then we will have D1, D2, for example, D equal, we reduce it to 3. Okay, for example, okay, this originally just the English letter, we have 24 dimension. Now we to reduce it to 3 dimension. Okay, everyone follow me? Know what I'm saying? Okay? Or I should put it further here. Let me put one more note. Okay. So we have D1, D2, and D3. And then we put all them together, which means it's called concatenation. Okay, we concatenate D1, D2, D3 with the real numbers variable S1, S2, and XP, and then we put it into another MLP. Okay, and we can run the output class to be Y1, Y2, and YC. So this we take a small. Okay, you can think of this as this is a sub MLP. Okay, this function is trying to use for what? For entity embedding. Let's say. Everyone follow me? Now, because a summation, you can use a method AE for. I'm sorry, right here. You can use the AE autoencoder for entity embedding. But what is the difference for autoencoder approach and this sub-MLP approach for entity embedding? What is the difference? What is the difference? Which could be better? Make guess. I have no answer. I didn't try it. I just asked you. 也就是说，你可以直接用 autoencoder 把1010的，然后呢， just extract right the hidden variable as your embedding code, or we can use the a small MLP, and then you can think of it just an encoder, there's no decoder. So we extract the features, okay, from this one-part encoded variable, and then we do the concatenation, 就把它串在一起了 ，concatenation 就把它串在一起了，没有加哈。So we have a D1, D3, D2, D3, X1, X2, and XP as the new feature vector. Then we input another MLP, a larger MLP. Then we do the estimate what should be the output based on the input vector here. Now, which one could be better? But what is the difference between the autoencoder approach or the small MLP approach for entity embedding? Anyone? Okay, talk about in Chinese it'll be fun. 这两个有什么不一样？有什么不一样？这个它只期待输入要等于输出。You just expect the output should be the same as the input. There's nothing to do with the class of the input sample. Everyone follow me? 它只期待输入跟输出一模一样，跟它这个样本的类别有没有关系？没有 ，because there is no information about the expected class. But for this one, the sub-NLP will learn something so that the output will be as accurate as possible to fit the expected output level. Y1, if it is class 1, then I expect Y1 should be 1, Y2 should be 0, and Y3 will be 0 again. Now the question is how to train this sub-MLP so that besides X1, X2, and XP, I also expect the embed the value or variable D1, D2, D3 will lead this MLP to have a better classification result. Everyone follow me? 也就是说，他这边他在训练这个的时候呢，他就有想到怎么让我的输出的类别的精确度呢越高越好。这边呢，他唯一要想的精确度只有什么？我要让我输出的值跟输入的值一模一样，就这样。Okay, and so which one will be better? It's all up to you. But if you think it could be too difficult for you to run or write to your own code, I don't know which one is better, but in Keras, there's a layer called embedding layer, okay? There's the embedding layer. You just call for this function. But it is different from this approach, okay? And that approach. So if your programming skill is good enough, I will recommend it just to run your own, or you can use the embedding layer provided in Keras. It will give you the lookup table. It will show you the lookup table. 它用查表。What does it mean by lookup table? Let's take the English letter as an example. Okay. And assume I use 3. I want to reduce the 26 dimensions, one-hot encoding, okay, variable into 3 real numbers, D1, D2, D3, Okay, now this is much easier, far much easier. Just you put 1, 2, 3, and up to 26. Okay, as an index, Okay, so 1 for A, 2 for B, and Z. Then during the training, whenever you apply the hidden layer, then your model, okay, or the course will try to learn what should be the D1, D2, D3 value for index 1. Then you will run another value for D1, D2, D3 that can be used for index 2. That's much easier, right? But which one will be better? I have no idea at all. Okay, so if you are interested, you can try it out for your project. But that's the way you use this. This is so-called the lookup table 查标法。为什么是查标法？它用什么？用1、2、3、4、5一直到26的里面那个值呢，当成指标。Okay? For example, you read out a value that could be 2, then you will go for here. And to read out this value, okay? This D1. Then you use it as the output for the one hard encoding. And then you concatenate with S1, S2, and then XP. Okay? Then you can do something there. Well, actually, if you want, you can even for example, you might have a time series data, okay, as the input. Then you go through a CNN. Well, I should put it. You put a CNN. Then you can read out the, not class, the feature, okay? You can read out the features. Then you can do the concatenate again with the categorical data with the real numbers data. See that? You know what I'm saying? You can put all that together, especially for medical application, for example. This categorical data could mean education level. Okay, 1 for elementary school, 2 for senior high school, junior high school, and so on. And this could be age, gender, weight, and height. And also, you might have the time series data for the vital sign, for example, or even you can have the image, okay, as the input, for example, the CT scan image or X-ray image, so that I'm trying to say it can, all the input data could be multiple types. It can be image, it could be time series, could be categorical data, or it can be any real number, integer value. But in the end, we try to extract the features and then we concatenate them all together into a larger feature. Then we put it into a classifier for further classification or for regression. That could be better. But anyway, when we talk about the random forest, the example method, I will talk about the should we go for this approach, or we should separate it into different classifiers? I mean, you can train time series with one classifier, image for another classifier, the vector value as another classifier, and then we input all the outputs into another method. That's called method learning, and to make the final decision. But for this case, and I try to say is, you can put all the multiple types of data together once it extracts the features. Okay, that's something you can do. Okay, so we can use MLP to handle the missing value and entity embedding for the vector value data. Okay, data. Okay, so as I mentioned, is unsupervised. Okay, that's good for the user. You only have to provide the input. Okay, and you will. What we need to focus is on the hidden, the features in the hidden layer. Okay, the hidden layer, and usually the number of nodes here or the dimension here is a hyperparameter. Okay, so you need to do your own experiment and to pick up the one that will fit your application. Okay. And here's that's if the input is vector value, then we go for MLP. If it's unstructured like image or time series data, then typically you can use CNN, as I just mentioned, LSTM or transformer. We have an encoder, decoder. Again, we use the output of the encoder as our features, okay? As our features, okay? So that's the typical CNN autoencoder for unstructured data. No matter it's image or series data, you need to go through a several convolution layer and then pulling for the convolution with the stride up to, okay? Anyway, you try to reduce the size. And how many layers will be enough? That will exactly just what I want you to do for assignment number 2, right? Remember, should the architecture should be wild or it should be dim? Okay, which one will give you the better result? And usually after the output, we'll do the flatten and do connect and do the fully connected, and then. The architecture here, you show you the hidden variable that will be used, okay, as our feature vector. And then we will do another fully connected and try to, if an image, you have to resize it from one dimension to dimension and then do what? To do the deconvolution, okay? Which is the convolution plus upsampling, okay? Again, as by a factor of 2, so that in the end the output size will be exactly the same as the input. Okay, no matter for image or for time series data, they are the same. The idea is the same here. Okay, so as I mentioned here, it does not or is not restricted for the CNN. It can be as a recurrent neural network, okay, or even transformer before. Okay. Okay, basically for autoencoder, the loss function we simply is measured by mean square error. Okay, MSE here's X the input, Y is the output. We expect we try to minimize the reconstruction error. Okay, but if Y, okay, or X, we interpret it as the probability because you can always use SOMAX, right? You can always use SOMAX. Then in that case, you can use a cross entropy. Okay, you can use the cross entropy. X is the input. We expect it should be a 0, 1, and this is the output. That's it. This is another expression. Okay, so it may not have to be restricted on mean square error. It can be also the cross entropy. That'll be fine. Okay, especially all the input and output interpreted as a probability. Okay, the probability. Then cross entropy will be another way that allow you to use. Okay. Okay. So that's it. That's about autoencoder, especially for convolutional autoencoder. Okay, as I mentioned here. For the convolutional, you just do the convolutional. You go through several layers Okay, convolutional and deconvolution. I will show you what do I mean by deconvolution later on. Okay, so that is simple. So this model is simple, and everything is based on MLP. If you are handling the vector variant data, or when you deal with the structured data, then just for time series data, then the convolution is got to be one-dimensional convolution, right? If the input is an image, then you go for the 2D convolution. That's okay. That's a CAE, okay, or autoencoder. Okay, remember, whenever we talk, I say something about autoencoder, which means we expect the output should be the same as the input. That's it, autoencoder. Okay, any question about so far? Okay, if not, now let's go to a more, a little bit, it needs some background about the statistics, okay, or probability, okay. That's another version of autoencoder, okay, called variational autoencoder, VAE. So usually we will select either CAE or VAE, okay, for our test, okay, CAE or VAE. Here's the idea, okay. The basic architecture is exactly the same, just like autoencoder or convolutional autoencoder. They are exactly the same. Okay? We still need an encoder. Let me put and decoder. The application, the objective are exactly the same. We expect the input or the output should be the same as the input, let's say, okay? And the model here, if the input is unstructured data, such as the image or time series data, you still can go for a CNN, okay? Convolution, just convolution, or transformer. They are all the same, okay? Like what I just mentioned. The only difference is the idea is here. We input X, I try to learn what should be the probability, okay, to maximize the Z. The Z here is called latent variable. Okay, it's not a single value. Actually, it should be a vector. It's a vector. You will learn a vector. That's called latent variable. Okay. X is given. Okay, because it's the input, something you observe. Okay, we observe the value. Then I want to know what should be the probability that you can have this latent variable Z. Okay, then given Z for the decoder is what? Now, given the latent variable, we try to maximize the likelihood for X, let's say, okay, based on the probability of that. 各位，你说基本上是根据距离。可是我讲过，这个模型呢，就是 convolution， 这边也是 convolution 哦，听得懂？它唯一不一样的就只有它所设定的条件不一样。它第一个是希望它有一个几率，我看到 x， 我要让它所呈现的这个有代表性的这个 latent variable 呢极大化，然后呢，根据我所猜的这个 latent variable 呢，我会看到还原成 x 的几率呢，以最大 OK， 它的目的就这样。OK， that's the only difference here. But it makes a lot of difference between CAE. OK, between CAE. When I say CAE means convolutional. OK, for unstructured data. OK, now we are talking about VAE. OK, variational autoencoder. OK. It's basically based on the variational inference, okay, to specify to technical, to professional. But anyway, the inference means what? I use the knowledge, okay, the inference here. I use the knowledge of X because X is something you observe. I use the information, okay, of the observed X, and then to find the information on the latent variable. That's called inference. Everyone follow? 也就是说，这个 inference 是说，我用我看到的 X， 这个 X 是你的样本嘛，你收集到的样本，我用他已经看到的这个样本的这些的 knowledge， 这些的资讯，我要去猜，那这个 Z 呢？这个 Z 我应该要怎么呈现 ？Okay， variational means is a optimization process. Okay, it's an optimization process using the let me see how to say it. Using the distribution from a chosen family. 也就是说哈，这个 Z 是什么我不知道。可是呢，我们现在试着在做是，它接下去这个是最佳化的过程。我是说，我要从一个比较容易掌握的几率分布里面，然后呢，为什么牵扯出来哈？这个几率，这个 family， 这个家族里，这个几率分布里面的那些参数呢，我要把它最佳化。Okay, everyone follow? Okay, variation is an optimization process. Okay, then you need to then you try to use a simple distribution. Usually it will mean Z. Okay, we use a simple distribution of Z. Then for this simple distribution, then we need to try to find the parameter from this family. Okay. Before I say anything, what will be the guess? What could be the good choice for this Z? I mean, from the probability distribution. If you have no idea at all, then you got to be Gaussian. Okay, got to be Gaussian because it's much the easy way to do this thing. If you have no information at all, always try to use. Throughout the whole semester, you will see this again and again. Okay, we simply just assume you follow Gaussian distribution. That's the idea of VAE. Okay, that's so-called the variational inference. Okay, now we can talk about it now. But basically, the architecture, the details architecture is exactly the same, just like CAE. But the objective or the loss function is quite different. I should not say quite different, a little bit different. Okay, the objective different, and the application will be a little bit different also. Okay. Okay, so. Now that's the idea here. Okay, that's the idea here. As I mentioned, we simply assume it comes from this the prior probability. We simply assume it's n means normal distribution or Gaussian a standard Gaussian distribution, okay, with zero mean and unit variance, okay. That's the idea, okay, and it work. You might wonder why, but it works, okay, for a lot of application. It may not work every time, but it just works. Okay, so I skipped a lot of details. Anyway, the idea is try to find the Latin variables, okay. Then it says here, it makes an assumption about the distribution of the Latin variable. As I put it here, if you have no other information, you have no idea at all, the most typical assumption, just assume it follow a standard Gaussian distribution. Okay, that's it. Okay. And okay, I skip the details. I give this example. This example is excellent. Okay. Now we have the. Image. I always, as I mentioned, the image is not the main focus of this course, but image is much easier to explain because everything can be visualized. Okay. So no matter for image or for time series data. We don't use it for vector value data. Okay, basically we don't need to do that. Okay, you can just use MLP. It'll be good enough. Okay, suppose the input is the image. Now the idea that the so-called Latin variable here. For this case, you will say something. The feature, this feature might represent the degree of smile. Okay, smile, the skin tone， 这个是微笑的程度了哈。然后肤色 the gender, okay, male or female, okay, with beard or without beard, okay, the person wear glasses or not, okay, or the hair color. I mean, it could mean something like this, okay. You might extract that Latin variable from this image, then you can extract some physical meaning, and then you assign the value for that, okay. Then we do then based on the Latin variable, we input it to the decoder, which is the generator. We try to generate the image, okay, on the objective that the output image should be as closer to the input image. And we have another term in the loss function. We will see that, okay, later. Okay, but that's a good, very good example, especially now here. It's right here. We have different picture. Okay, this kid looks a little bit sad, right? A little bit sad. So for the smile, that variable here, if you go for the CAE, then you might have the value here, negative value for the degree of smile. But for VAE, you will output the distribution. See it? Okay? You will give it the distribution. But anyway, the mean will be less than 0. But it won't give you the exact, okay, a crisp value, okay, just like CAE, just give you some the discrete value. But instead, for VAE, we'll give you the distribution, okay, a distribution. Now, for Mona Lisa, as you know, everybody knows, I don't know if she's smiling or not. Okay, so for this case, just assume the mean of the Gaussian distribution is 0. Okay, it could be so different person will may have a person perception. Okay, and for this one, definitely she's laughing a lot, so the mean could be higher. Okay, so that's how it runs. Okay, how the learn distribution. So it's so quite different from the crystal value. It just once you learn it, the value is fixed. Okay, it means what? Whenever I input this picture to a CAE, you always will get the same hidden variable. But when you input exactly the same image into the VAE, every time you will see a little bit different. Okay, that's something you need to watch out. Okay, you may not always get exactly the same. You may not tell the difference visually, but the value will not be exactly the same because it's based on the sampling from the distribution. Okay, it's based on the distribution. Okay, that's PID. Now, just give you a few more seconds here. Okay, so for this input, then you are trying to express it with a different distribution value for that. This give you the example. This is from Fifty's class note. Suppose we have two hidden variable here. Okay, Z1, Z2. See that when you change the value for Z1, it means what? Then you will change the degrees of smile. See that? Okay. Then when you change the value of Z2, then it will show you different paid cost. It turns from left to right or right to left. See that? That's how we can manipulate. So basically, VAE is used as a image generator or signal or data generator. Okay, not like CAE. Okay, a little bit different from the CAE. CAE just trying to find or for dimension reduction, but VAE most of the time it has been used as a generator. 它是一个产生器，听得懂？它可以产生不同的影像，产生不同的时序信号，因为它里面你可以透过去操作它的这个 latent variable， 你可以得到不同的影像，会有点不一样。OK， 那是它的目的。好，我们休息一下。OK。